So this video is going to review what we know about threshold. So we talked about threshold in class, and threshold is basically the definition of how much ligand is required to create a response in the cell. And so if you have a low threshold, you don't need as much ligand to recreate a response. If you have a high threshold, more ligand is needed to create a response. So if we see the graph down here in the lower right, we see that as the amount of ligand increases, the threshold is the time at which the amount of ligand required to create a signal and get a response. And so we can see here in D that D has the highest threshold and A would have the lowest threshold because it needs the least amount of ligand in order to create that response. And we talked about two main things that really affect threshold. And we know that all signaling events require a ligand bound to a receptor, then requires a conformation change in that receptor that's perceptible to the inside of the cell, and then that leads to signaling cascade and ultimately the response. But the two things that really control threshold are the receptor's affinity and the number of receptors. And this is often referred to as the concentration of receptors. And we know that as the affinity goes up, that means there is tighter binding. And if there's tighter binding, it's more likely that the ligand is going to bind to the receptor. So as affinity goes up, threshold goes down. You don't need as much to get good binding to the receptor if the affinity is high. And if you have more receptors, there's also more of a chance for some ligand to bind, and so the more receptors also causes the threshold to go down. Now, the one thing we need to remember is that in chemistry, most of the quantification of this in terms of affinity is defined as Kd. So Kd is simply the measure of how much of that ligand falls off. Basically, it's how much ligand do you need for 50% of the receptors to be bound. All right, but really another way to state that is how easily does that ligand fall off. So if you have high affinity, tight binding, it's not going to fall off as easy. So we know that Kd has the inverse relationship to affinity. So as affinity goes up, Kd actually goes down. And this is why Kd has a direct relationship to threshold. In other words, as Kd goes down, so does threshold. Or if Kd goes up, so would threshold. So here we have, in this table, we have a list of values for 4 different conditions. And we want to figure out which of these values in the graph, A, B, C, and D, associate with each one. So you basically just take one of them, I usually just use the top one by default, and use that as your baseline. So this is going to be my baseline here, and I'm just going to figure out how much each is changing from that one. So we can see in terms of the number of receptors, as we go from that one, from the 1.0 micromolar to 0.5 micromolar, we have gone down by 2-fold. In other words, we have a 2-fold decrease in the amount of receptors. And so if the number of receptors has gone down 2-fold, we know that this makes the threshold actually go up 2-fold. So the threshold from my 1.0 micromolar to my 0.5 micromolar has caused the threshold to change by going up 2-fold. In contrast, if we look at the difference between the 1.0 micromolar and the 2.0 micromolar, this is a 2-fold change also, but this 2-fold change in the amount of receptors is going up. It has 2-fold more receptors. And so as the number of receptors goes up, threshold goes down. So my threshold has gone down 2-fold from the first one to the third one in that regard. And then finally, for this one here, we have a 4-fold increase in the number of receptors, which is going to mean my threshold is decreasing by a factor of 4. All right, so Kd, we just basically do the same thing. We see that the Kd here has gone down 3-fold. From 3 to 1, the Kd went down, so down 3-fold. And if Kd goes down, well, so does the affinity. So that brings if Kd goes down, so does the threshold. So my threshold has just gone down 3-fold there as well. And from this one, from the first to the third is the same thing, so that also has gone down 3-fold. And then from the baseline to the fourth one, we've actually gone up twofold in the KD, so my threshold also is increased twofold based on the KD there. So now we know that the contribution of threshold between the concentration of the receptors and the KD is equal. So now we just figure out the net change. And so went up 2, down 3, that yields a net of down 1. We went down in the second one here, we went down 2 and down 3, that yields a net of down 5. And in the last one here, we went down 4 and then up 2, so that yields a net of down 2. So if our baseline is considered the 0, all 3 of these have gone down. So that means this one actually must have the highest threshold. All right, so this one is D. The next highest threshold is the one that went down the least compared to the others. So this one has the next highest threshold, and so this one would be C. This one would be B, and this one has the lowest threshold. It went down the most. That one right here is A. So now, based on doing this, we can figure out that which of these graphs corresponds to each of those values.